Hello everyone, my name is Ousmane and I'm assistant professor at McMaster University. Prior to that I was at Sherbrooke University where I did this work with my co-author Alasgi Ternidamu. My presentation is on nano-engineering the interface properties of PVA fibers in strain-hardening cementitious composites. We will go through these points during our presentation. So let us first of all define nano-engineered concrete. The most straightforward definition is the one that links the different concrete classes to the specific surface area of their ingredients. You can see here that from normal strength concrete to ultra high performance concrete that has further effective silica film that has much finer particles, to nano-engineered concrete with much finer materials and higher surface area, of course. So here the nanocellulose materials we are working on fall in this with significantly high surface area as well. And most importantly, what makes them unique is their abundance. More than 50% of the Earth's biomass is nanocellulose, and also their reinforcing ability that imparts intrinsic strength to plant-based materials. A reinforcing ability that spans several length scales from the atomic level upward to the metric level scale, the tree scales. So the idea is to leverage the reinforcing ability of nanocellulose to make strain-hardening cementitious composites more ductile by imparting a nano-reinforcing mechanism that makes these SHCCs more like multi-scale reinforcing. As you know, everyone knows that cracking in concrete is a multi-scale that has nano crack zone, micro crack zone, and macro crack zone. So mitigating cracking at the macro and micro level as traditionally being done is not enough. The work that's being done now with this committee, nano-engineering concrete, nanotechnology concrete, will drive the enhancement of crack resistance at the nanoscale level, as you can see. So, in strain-hardening cementitious composite is the one that once the first cracking occurs, rather than the abrupt failure in the plain concrete, nor the softening in conventional FRC, SHCC will go to taking significant load and multiple cracking phase, and before coalescence of cracking, some high tensile strength capacity that exceeds 60 times that of plain concrete. So the idea behind this design philosophy is that there are two things to be satisfied. The first thing is that the bridging capacity that's provided by the mainstream fibers, and here we talk about PVA fibers that are used in SHCC. So these PVA fibers have to provide a bridging capacity that needs to be higher than the first cracking strength of the mix, and this is quite common to all FRC. However, the second requirement is that once the plain matrix cracks, the advancement of the crack and the energy of the crack has to remain smaller than the complementary energy which is guaranteed by the bridging capacity. So usually these materials are formulated using fly ash. However, fly ash is vanishing due to the phasing out of energy plants that are based on coal. An option is ground glass. The research group of Technique at Sherbrooke has been working on glass powder since for a decade, and the material has now been standardized in Canadian standards and ASTM, and has been used in normal concrete, but its use in innovative concretes is on the way. So you can see here that we use these PVA fibers with these properties, and we use nanocellulose fibers with those properties, and the material was provided by our industry partner, Kruger Biomaterials. So the methodology goes two lines. The first thing is to engineer the compactness. I mean to enhance, to optimize the compactness of the matrix from one side, but also to nano-reinforce the matrix from the other side. So the compactness was enhanced through replacement of the fly ash. It's here in the SHCC formulation. We have the sand, we have ground glass, we have fly ash, and we have cement here. So we replaced fly ash with ground glass at increasing levels, and this enables filling the particle gap. You can see here that in these particle size solution curves there is a particle gap existing between the sand from one side and the cementitious material from the other side. And by replacing fly ash with ground glass, we were able to fill this particle gap and leading to higher compacity. That's reflected by this much more wider and much more graduated particle size solution. So a well-graded particle size solution, better particle size solution gradation was obtained by this replacement, and this led to higher capacity, as you can see in this slide. So at increasing level of ground glass placement fly ash, we obtained higher packing density. However, the higher packing density has been reflected by higher frictional bonds. You can see here. The frictional bond was characterized by single fiber pull-out test. This is a matrix that has PVA fibers embedded in during the first state, of course. So the PVA fiber has an embedment length of 1 millimeter to ensure that it will be efficiently pulled out. The installation of the fiber was very tedious, meticulous process, so that we got exactly straight fiber, non-inclined. We haven't detailed all of these here for the sake of brevity. So pulling out the fiber, of course we have here 2 fibers per every piece here, such that if this one fails, we could still pull this fiber out. And for every test we have, for every mixture we have almost like 10 tests for every mixture to ensure that we have repeatability. So we have here the frictional bond, which is calculated by this formula. The applied load over the embedment length time is the embedment area. Here you can see here that the chemical bond, the frictional bond, and so on. So you can see here that the addition of ground glass from 0 to 100% has increased the frictional bond. This increasing frictional bond is a direct consequence of the higher compactness that we saw in the previous slide, and higher compactness leads to higher tightness of the interfacial zone. And as a result of this higher compactness, higher tightness, higher frictional bond, we ended up having higher bridging capacity. This is a bridging capacity. This axis is bridging capacity, and here this is crack opening. And due to this drop, you can see here that the curves are having higher bridging capacity, but the crack opening corresponding to the maximum bridging capacity is getting lower. The crack opening is getting lower as we get higher ground. This is because the matrix is becoming stronger, brittle. So this leads to lower complementary energy. As we see here, the complementary energy is becoming lower with higher glass powder content. Therefore, you can see here that when we verified and validated this results by uniaxial tensile test, we obtained higher direct tensile test, as you can see here, up to more than twice higher uniaxial tensile resistance. However, you can see here that the tensile strength capacity has dropped as well. So up to 40% glass powder content replacement of fly ash, we are still okay in terms of ductility. The strength has increased significantly, as you can see here, but the ductility has dropped. And the drop in ductility is even worse when we go to higher ground glass content, even though the tensile strengths are significantly high. So when we go at the microstructure scale and we see, in parallel to the increment in the glass powder content, which is accompanied by higher frictional bond, we can see that the pull-out mechanism is characterized in the reference with such a configuration, such a behavior. While when we go to higher glass powder contents, you can see higher damage, higher likelihood of fiber damage, and this is as a result of the tighter interfacial zone due to stiffer matrix and also much more friction. So the idea here is that when we use nanocellulose materials to reinforce either the matrix that does not have glass powder, which is the reference, or the matrix that has glass powder from 0 to 100%, there will be a nano-reinforcing effect on the matrix as well as on the fiber matrix interface, PVA fiber matrix interface. And that's what we can see here. By selecting 3 classes of SHCCs that we tested here, the reference one does not have glass powder versus the 40% glass powder SHCC and the one that has 100%, and incorporating solid filaments at those levels on those classes of SHCC, we can see a twofold effect here. There is one effect on the matrix. You see here that the matrix is now being meshed at the nanoscale, but also we can see the PVA fiber, the channel that you see here, which is also here, is now like meshed. There is an effect here of the nanocellulose material at the interface here, as you can see, as well as creating an interface between the matrix and the PVA fiber. And you can see here that several nanocellulose filaments are covering the PVA fiber surface. So by creating this polymeric interface between the PVA fiber and the matrix, there is now alteration in the interfacial frictional mechanism. You can see here that in this matrix that does not have glass powder, the frictional bond remained as it is. It did not change a lot because the frictional bond was not that significant even before the addition of cellulose filaments. So by adding cellulose filaments in this matrix, we did not see a significant change. However, by adding cellulose filaments to the matrix that has 40% glass powder, or the matrix that has 100% glass powder, you can see that these bars in black color are now dropping, which is the effect of the interfacial polymeric interface that is now created in the presence of cellulose materials. We ended up having lower frictional bond. The slip-hardening, importantly, has changed a lot. You can see that we have significant slip-hardening in all of those cases, which is due to a jamming effect in the presence of cellulose materials surrounding the PVA fiber at the channel, the fiber channel. You end up having a jamming effect that resists the pull-out of the fiber, while the interface created by these nanomaterials, nanocellulose materials, reduces the friction, as you can see. So, as a result, the fiber bridging capacity has remained the same, but the complementary energy has significantly enhanced. You could see here that in the system that does not have ground glass, we are here. By adding cellulose filaments in this system, you can see that the curves have shifted to the right, although the peak did not change a lot, and this is quite persistent in all of these systems. So this has a direct consequence on the tensile strain capacity, tensile strength and strain capacity. You can see from the systems that have 0% glass powder to 40%, 100%. Prior to adding cellulose filaments, we are at this scale, and by adding cellulose filaments, you can see here that the tensile strain capacity has changed significantly, particularly in systems which were originally brittle. 40% and 100% ground glass systems were significantly brittle in the beginning, and adding the cellulose filaments, which did a twofold effect on the matrix by making the matrix more ductile, and also on the interface by creating a polymeric interface between the PVA fibers and the matrix. There is higher tendency of strain hardening at the individual fiber pull-out. So the individual fiber pull-out is no longer like strain softening, but it's more strain slip hardening, which is reflected now at the composite level as higher strain capacity, as you can see here. And the matrices, which had 100% ground glass, which were initially brittle, were the best to benefit from the addition of cellulose, which rendered them much more ductile. At the flexural testing scale, you could see here that these systems can show a ductile-like behavior after several excitations, repeated excitations, even after cracking, by the way. Under these supports, in-person observations showed cracking, significant cracking appearing here at these, especially at these supports, but at this load application point, I would like to say load application points, but the resistance will change. So we end up saying here that using ground glass in replacement of fly ash, new strain-hardening cementitious composites, more environmental friendly, were obtained. The replacement of fly ash by ground glass was limited to 40% because of the significant brittleness that comes with the ground glass addition. However, by adding nanocellulose, we were able to make the system much more ductile, because at higher capacity obtained by ground glass addition, there is tendency to even damage the fiber. The fibers get damaged easily due to the tighter interfacial transition zone. By adding nanocellulose, there is a twofold effect. The matrix becomes multi-scale reinforced, nano-reinforced, and also the interface became much more a polymeric interface, meaning a less friction that leads to enhancing the pull-out of the individual fibers. Individual fibers pull-out is in the presence of nanocellulose became much more slip-hardening pull. And that slip-hardening pull was reflected at the composite scale at the slip-hardening behavior at the composite level. And this has led to much ductile composites as reflected by and verified by uniaxial tensile tests as well as in texture. That's all what I have for you. Thank you for your attention, and thanks also to our partners. And if you have questions, you could send them by email. I will be glad to respond to you. Thank you a lot.